All right, welcome everybody. Today we are going to be talking about buoyancy. So, what is buoyancy? Buoyancy, or upthrust, is an upward force exerted by a fluid that opposes the weight of a partially or fully immersed object. So, here's a quick history of buoyancy. Archimedes was the person who discovered buoyancy. Archimedes was a Greek man from the city of Syracuse. So, Archimedes discovered buoyancy while bathing. Archimedes noticed that the water level rose as he got into the tub, and he was able to calculate the tub's volume as the water increased, therefore discovering buoyancy. By dividing the mass with the volume, he was able to find density as well. And this discovery led to a famous principle called the Archimedes principle. And here we're going to talk about Archimedes' principle in this video.
So let's go ahead and derive Archimedes' principle. First, we're going to want to understand what the variables are and what they mean. First here we have F sub b, or the force of buoyancy. The force of buoyancy is an upward force that the water applies to an object in the water. Rho sub F, which is the fluid density. It's the how massive the fluid is compared to its volume. Every fluid has a defined fluid density. For example, for water, it's 1 gram per milliliter. Next up, we have the mass of the fluid that is displaced by an object placed in it, and the volume of the fluid displaced by an object placed in it. And then last, we have acceleration due to gravity, g. These are the two main ones we're going to want to be focusing on. So let's go ahead and derive Archimedes' principle over here. We start with our two main equations. F equals ma, or in this case would be force of buoyancy equals the mass of displaced fluid times the force of, or the acceleration due to gravity, and the density equation, rho equals the mass of the displaced fluid over the volume of the displaced fluid. So if we substitute, or if we solve for mass in this density equation and plug it back into our Newton's second law equation, we get the force of buoyancy equals rho times the volume times gravity. And it's all negative because the force of buoyancy is an upward force while gravity is accelerating down. Now we're going to talk about water displacement as an object is getting submerged into the water or any fluid. So, as seen in these diagrams, there's a base water level before it gets submerged, but as this red boat starts to get submerged into the water level rises. And that water level rising is water being displaced by the boat. And so as the water keeps getting displaced, it'll eventually get to the point where the boat is fully submerged and it'll reach its maximum water displacement by volume and mass. So here are some little explanations of those. It starts out with no water displacement, and then water displacement increasing as the object is getting lower in the water, and then a maximum water displacement, and that can't change no matter where the boat is as long as it's fully submerged. So, as we know from our previous equation, Archimedes' principle, the volume of displaced water, or any fluid, directly impacts the buoyancy force. So, once we get to a maximum displaced water, we also reach a maximum buoyancy force, which is why if our buoyancy force maximum, so when something's fully submerged, the buoyancy force on it, is greater than the force of the weight, something will float. But if it's less than it, it will definitely sink.
All right, now that we learned about Archimedes' principle, it is now time to learn about the net force principle. And here we go.
So we're going to go over 3 methods for how to see if an object will sink or float in a fluid. In all 3 examples, we'll be using water. So first, in this first method, we're going to be using the net force principle we just talked about. F net equals the force of the weight of the object minus the force of buoyancy pushing up against it. So we find the force of the weight of the object, which is, we can calculate from the given mass and volume of the object, and we calculate that at 1 Newton, for example. Then, to calculate the force of buoyancy, we plug in our known fluid density for water, which is 1 kilogram per liter or 1 gram per milliliter. We plug in 10 meters per second squared for gravity, and for volume, as this method is just a test if the ball will float or sink, we will plug in the volume of the ball, because if the ball is fully submerged and doesn't displace enough water to make itself float, we will get a positive force here. Otherwise, we'll get a negative force. So we're going to plug in the volume of the ball here, the maximum amount of volume that can be displaced by the ball. So, and that gives us 2 newtons. So if we go back to this equation, we get F net equals 1 newton minus 2 newtons, which is, the net force is minus 1 newtons. This is an upwards net force because it's negative, which lets us know that the ball is going to float because, the net force is upwards, it's just going to stay up. The second method we'll be using also uses the net force principle. F net equals the force of the weight of the ball minus the force of buoyancy, where the force of weight is that same 1 newtons we calculated earlier, and the force of buoyancy, we will actually not be plugging in the volume of displaced fluids yet. So we get the volume of displaced fluids as a variable times 1 kilogram per liter times 10 meters per second squared, which comes out to newtons. So we go back to this equation. F net equals 1 newton minus 10 times the volume of displaced fluid, and we're going to assume that that's equal to 0. And the reason we're going to assume that's equal to 0 is that we're going to assume that the ball is floating in this example, and we'll be able to check if it is or not when we get our answer of our volume, but we're going to go ahead and assume that this is 0. So next thing we're going to do is we're going to solve for the volume of displaced fluid by the ball. And it's pretty simple here. 0 equals 1 minus 10 times V. The volume of displaced fluid is 0.1 liters or 100 milliliters. Now, because this 100 milliliters is less than the 200 milliliter mass of the ball, we know that the ball can displace that much water, which means that the ball will float, because it can displace that much water and get enough buoyancy force to stop itself from sinking. And we also know that as the ball goes into the water and the buoyancy force increases, we know that the ball will stop sinking once half of it is submerged. Once 100 milliliters of the ball has been submerged and that much water has been displaced. So we know now that the ball will float and will be half submerged in the water. Our third method is much simpler, and we don't use the net force principle. So what we do is we check if the density of the ball is less than or equal to the density of the fluid it's in. Again, we're using water in this case, which is 1 gram per milliliter, and we can calculate the ball's density using its mass and its volume. So we take the density of the ball equals 100 grams over 200 milliliters, and we get the ball's density is 0.5 grams per milliliter. We check again that 0.5 grams per milliliter is less than or equal to 1 gram per milliliter, which lets us know that the ball will float as it is less dense than the fluid it's in, so it will rise.
All right, now that we know about Archimedes' principle and the net force principle, it's time to put these into use and find out some real-world examples.
All right, let's go ahead and look at some real-world examples. We're going to be looking at 2 things here. We're going to be looking at rubber and plastic in comparison to water. So as you can see, water has a density of 1 gram per milliliter, rubber has 1.34 grams per milliliter, and plastic has 0.91 grams per milliliter. Now, according to the previous method we recently discussed on method 3, we could see that in comparison that water has a lower density than rubber, and H2O has a higher density than the plastic. So according to this, if we're going to test it out, if we're going to put some water in the cup, the plastic should float under this condition, in which it does, and then the rubber should sink. As easy as that. And this was a real-world example of how we can use this and analyze different densities in comparison to water.
All right, so in conclusion, buoyancy is an extremely important force and it is necessary for flotation. So, for example, no matter how large a ship is, it'll always rely on the force of buoyancy to keep it afloat. And in order to understand buoyancy, you must know the Archimedes principle and net force principle. And for anyone wondering, these are the sources that we used for this project. If you would like to do some more further research, these are some great sources. Thank you guys so much for listening.